Hey everyone, and welcome back to this series on elementary probability and statistics. In this video, we're going to continue our discussion on discrete random variables and probability mass functions that are defined on them. In the last video, we briefly discussed two operations that are commonly defined on discrete random variables, in particular the expected value and the variance of them. In this video, we're going to derive a few important properties associated to them, and also talk about the covariance and the correlation between them as well. Once we're done, we're going to give you a few exercises to test your understanding. Let's get started. Alright, so let's just briefly review what we mean by the expected value and the variance of random variables, in particular the discrete kind. So we're going to begin by letting x be a discrete random variable. Therefore, we define the expected value of x to be equal to the sum of all x times the associated probabilities for that particular value, and this is going to be for all values in the support of our probability mass function, x. Similarly, the variance, actually before we get into the variance, let us define the second moment of a random variable x. So this is typically defined similar to the expected value, but instead of x, we're going to be squaring the x values and then multiplying by their associated probabilities. Still, this is going to be true for all values in the support of that particular function. And from these two, we can define the variance of that random variable to be equal to the second moment of that random variable minus the square of the mean of that random variable. Also keep in mind a couple notational differences here. Some people will abbreviate ex by mu of x because it's the mean of that random variable. And some people will denote the variance of this random variable by sigma sub x squared. Those are the same exact thing. In terms of whether you choose one or the other, it really depends on what you're trying to advertise to your audience. So let us talk about a couple properties that are associated to the expected value, for example. That's usually the easiest. And then we're going to get into some discussions on the variance as well and its properties. So let us assume we have a particular number. Let us assume A is a real number. It can be a complex number, but typically when we work in statistics and probability, usually we work with real numbers only. So then we're going to consider the random variable A times that random variable. So you can sort of think about this random variable as you have a data set with a bunch of values and you multiply all those values by a particular number like 5. So of course the original data set had a particular mean, and once you multiply all of those numbers by like 5, then the mean is of course going to change. So what is going to be the mean of that particular random variable, and can you get it from the original mean? In fact, you can. So one can prove that the expected value of a constant times a random variable x is actually equal to that same constant multiplied by the original expected value. Similarly, if you have some values in a particular set x and you pairwisely add them to another set y, and then you take the average of the sum of those values, you can find that that's actually going to be the sum of the original means. This property is a little bit more involved to prove, at least from the definition of expected value. But if you're familiar with probability mass functions or probability density functions, the multivariable kind, the proof is actually quite straightforward. So let us do a quick example of why we would care about something like this. So let's look at a particular example. So let's go with let x and y be random variables such that the mean of x is going to be equal to 3 and the mean of y is going to be equal to 5, right? So the mean value is 3, mean value is 5 for x and y respectively. And we're going to define a new variable, let's say r, to be equal to 5 times x plus 7 times y. Now, why would you want to do this? Well, you can sort of think of this like a revenue function. So you charge $5 for every unit of x you sell, and you charge $7 for every unit y you sell. So the number of units you sell of both x and y are random variables, so the revenue is going to be a random variable as well. So this pretty much says the average number of units of x that you sell is 3, the average number of units you sell for y is 5. Therefore, on average, what will be your revenue on a particular, say, day or something like that, right? So when we say this, what is mu of r? This is the same as what is the expected revenue of R. The mean revenue and the expected value of revenue is the same thing from the statistical and probability context, right? So R, by definition, is going to be equal to 5x plus 7y. So we already know that 5x and 7y are random variables, and expected value distributes over sums with no issue. So this is going to be equal to the expected value of 5x plus the expected value of 7y. So again, 5 and 7 are constants, so they can be factored out of the expected value operator. So this is just going to be equal to 5 times the expected value of x plus 7 times the expected value of y. So we already know the expected value of x and the expected value of y are going to be 3 and 5 respectively. So this is just going to be equal to 5 multiplied by 3 plus 7 multiplied by 5. So once we have that, we have 5 times 3 is going to be 15, plus 7 times 5 is going to be 35, and 35 plus 15 is going to be 50. And let us assume this is in dollars. That means our expected revenue is going to be $50 based upon the information that we're given here. Okay, so that's a nice little property of, and sometimes we call this a linear combination of random variables. So a linear combination of random variables. And expected value across linear combinations is actually pretty easy. What's not so easy, for example, what if you have like a revenue function such that it's like, 5x minus 2y plus 3xy. Now this term is going to give us a little bit issues because we don't exactly know that the expected value of the product is equal to the product of expected values. And in general, that's not true. So we need to figure out a property that's sort of associated with that. And before we get into that, I just want to review joint probability mass functions, just in case you've never encountered them or maybe you need a little bit of practice on them, okay? So consider the joint probability mass function. I'm going to call it P on random variables x and y. And this, is, of course, is a probability mass function, or PMF for short, on two random variables, so I need to use a table to define it. Okay, so let this be 2, and let that be 1 and 2, and let this be 3 and 4. So y can take values of 3 and 4, and x can take values of 1 and 2. So let's assign some probabilities to these. So let's this be 0.1, 0.2, 0.3, so that's going to be 5 plus 6, so that's going to be 0.4. So you should be able to see that the double sum across all values x and y for this particular function should be 1. Therefore, this is indeed a probability mass function because the sum is 1 and all of the values in there are between 0 and 1. All right, so what I want to do is calculate, let's do a couple things here. Let's actually calculate what we call the product moment, this EXY term. So by definition, this is going to be defined as the sum across all x, the sum across all y, of the product of x and y times the joint probability mass function evaluated at that particular point. So this is actually pretty simple. So we just need to go across this whole entire table and do the sum product of all these values. So this is going to be equal to 1 times 3 times its corresponding probability plus 1 times 4 times its probability. And then we're going to have 2 times 3 times its probability, and then finally 2 times 4 times its probability there. Okay? So let's do some basic arithmetic. So 3 times 0.1, that's going to be 0.3. And 4 times 0.3, that's going to be 1.2. 3 times 2 is 6, and 6 times 0.2 is 1.2. And 2 times 4 is 8, and 8 times 0.4 is going to be 3.2. Right? So we have, what do we have here? So this is going to be 2.4. This is going to be 2.7. And adding that together, that's going to be, 5.9? So 5.9 is going to be, some people call this the product first moment of the random variables x and y. So that's wonderful, right? So why do exactly do I want to introduce this particular concept? So for me here, I'm going to introduce the concept of covariance between the random variables. So covariance between two random variables. And this formula is also going to be the same for continuous random variables as well, but we're just focusing on the discrete for now so we can get familiar with the notation. So the covariance between two variables x and y is going to be equal to the product first moment of x and y minus the product of the individual first moments, ex and ey. So another definition that I'm just going to add here. So we say that x and y are independent if the probability of x and y, so this is just a review from probability theory, the probability of x and y is equal to the probability of x times the probability of y, and that's for all possible values x and y for which they can hold. Okay? So if exy is equal to ex times ey, then we can say, and we can easily prove this, that means x and y are independent random variables, right? That is, their covariance is equal to 0, or at least they appear to be independent, right? All right, wonderful. So let's continue this example that I have up here. So 1, 2, 3, and 4. So 1, 2, 3, and 4, and those probabilities were easy to remember, right? So 0.1, 0.2, 0.3, and 0.4. So this is x and this is y. That's my probability mass function. And I already found that my product first moment was equal to, what was it, 5.9? Great. So now what I want to do is go ahead and calculate my covariance between these two random variables and see if they are independent or not. So the first thing I need to do is calculate the mean of x and the mean of y. So what is the probability that x is equal to 1? So the probability that x is equal to 1 is going to be the sum across the rows of all possible values of y. So that's going to be equal to 0.4. And the probability that x is equal to 2 is going to be equal to the sum across the rows of 2, so that's going to be 0.6. Keep in mind that these values should sum up to 1, and this table is sometimes called the marginal probability mass function for the random variable x. Okay? We can do the similar thing for y. So what is the probability that y is equal to 3? It can't be equal to 1. It can only be 3 and 4. So that's going to be the sum of the first column. So that's going to be 0.3, and the probability that y is equal to 4 is going to be 0.7. That's the sum of the second column, right? And clearly the sum across all values here must be equal to 1, and we call this table the marginal probability mass function for the random variable y. All right? So now I can calculate the mean of x and the mean of y independently. So that's wonderful. So clearly the mean of x, or the expected value of x, is just going to be the sum of the x values times the marginal values at x. So that's just going to be equal to 1 times 0.4 plus 2 times 0.6. So that's 0.4 plus 1.2, so that's going to be equal to 1.6. So that's the mean of x. Similarly, the mean of y, or the expected value of y, is going to be the sum of the y values times p of y. So that's going to be equal to 3 times 0.3 plus 4 times 0.7. So that's going to be equal to 0.9 plus 7 times 4 is 28. And then when I add those together, I get, what is that? Add 10, that's 3.8, so that goes to 3.7. Okay? So those are the mean of x and the mean of y. So let's calculate the covariance here. So the covariance between x and y, remember, is going to be the product first moment minus the product of the individual first moments, ex and ey. Okay? So that's going to be equal to what? So that's going to be equal to 5.9. So we have 5.9 minus 1.6 multiplied by 3.7. Clearly that doesn't appear to come out to be 0. I can just calculate that just to make sure, but I'm pretty sure it's not. It's going to be 5.92, so we have a negative covariance. So we have 5.9 minus 5.92. So when I subtract 5.9, I'm going to have negative 0.02 as my covariance, right? So as one increases, it appears that the other decreases. And I clearly built my table according to that type of approach. So since the covariance is not equal to 0, that implies they are not independent. random variables, right? So that is just an overview of some of the basic properties associated to the mean, and a brief overview of how to calculate the product first moment and the covariance of random variables. So we're going to use this concept of covariance to build the properties for the variance between random variables. So let's take a look at that. All right, so here's just a brief overview of what we've discussed so far. So I have the expected value, the second moment, and from them we can get the variance very easily. We have the product first moment, and also the covariance between random variables, and some properties associated to independence between them. So we've already proven these two properties for the expected value, the constant rule and the random variable rule, if you have two. And keep in mind, this is true for all random variables x and y. So x and y can be independent, they can be dependent, they can be mutually exclusive. We do not care. This rule always holds. So that's an important thing that I want to keep in mind. In addition to the covariance, sometimes we also talk about the correlation between random variables. And typically we denote that by Greek letter rho of x and y. And this is defined to be equal to the covariance between the random variables divided by the product of the standard deviations of x and y. And in case you don't know how to find the standard deviations, you just simply find the variance between them and then take the square root. So one important property about the correlation between random variables is that this number must always be between -1 and 1. That's one of the special properties of it. We're not going to prove that property here, but if you want to just practice calculating that, you can continue with the last example that we just had and go ahead and calculate the correlation between those random variables. So now what I want to do is build two or actually more important properties associated with the variance between random variables. So let's take a look at that, and I'm actually going to go through the proof for each of these because it's actually going to be extremely helpful to derive some properties that we're going to use a little bit later. Okay, so let's figure out a similar property for property 1 that we have for the expected value of a constant times a random variable. So property 1 for variance. What is the variance of a times x? Is it equal to a times the variance of x? So if you take all the values in a particular set and you multiply all of them by 5, if you know the original variance, is the new variance going to be simply 5 times that? Actually, no. So using the properties of variance and how we typically calculate that from the second moment and first moment, we know that this is going to be equal to the second moment of that random variable minus the square of the mean of that random variable, right? So that's usually how we calculate this. So let's just do a little bit of math. So we know ax squared is the same as a squared x squared. And we know by properties of expected value, this a can be factored out. So that's just going to be equal to a times e of x, the quantity squared. Keep in mind, ex is just a number, so the square can just distribute to each of them. And also this a squared can be factored out. So notice that both of them are going to have an a squared term. So we're just going to be left with a squared multiplied by the second moment of x minus the square of the mean. So what is this? Well, that's precisely the variance. So this is going to be equal to a squared times the variance of x. So what does that mean? So if we have an original variance of like 3 and we multiply all of the values by 5, the new variance is not 5 times 3, it's 5 squared times 3, or 25 times 3, which is 75. Okay? So in a way, this a cannot be factored out of the variance, it quadratically factors out of the variance, right? So the variance of ax is the same as a squared, the variance of x. Super important. All right, so just a side note, just in case you're curious, what about the variance of, for example, negative 3x, right? Can variance be negative? Typically not. So notice when we quadratically factor this negative 3 out, that's just going to be negative 3 squared times the variance of x. So that's just going to be 9 times the variance of x. So still, it's going to be a positive number, so no big deal there. So don't be scared. So the variance of ax and negative ax are going to be the same. Fun property to prove. So what about the variance between the sum or difference of random variables? So this is important. So the variance of x plus y. So let's just do it in the same way. So the expected value of x plus y squared minus the square of the expected value. Okay? So I can square x plus y, that's no big deal. So that's going to be the expected value of x squared plus 2xy plus y squared. And expected value distributes over sum, so that's no big deal. So we're just going to have expected value of x plus the expected value of y, the quantity squared. Notice that these are random variables, these are numbers. Make sure you know the difference between the two. And we know that these are all random variables, so we can distribute the expected value over each of them. So that's just going to be equal to the expected value of x squared. 2 is just a constant, so I'm just going to factor that out. So I'm going to have 2exy plus ey squared. And then I'm going to square that and then distribute the negative after. So that's just going to be the square of the expected value of x minus 2 expected value of x, expected value of y, minus the expected value of y, the quantity squared. Now I'm going to rearrange, so I have the expected value of x squared minus the square of the expected value of x. That's just the variance of x, right? And then the expected value of y squared minus the square of the expected value of y, that's just the variance of y. And then I have this other thing here. That's not quite anything I know because I have this 2, but I can factor that 2 out and you should see something very familiar. So this is just going to be equal to the variance of x plus the variance of y plus 2 times this quantity exy minus ex times ey. And what exactly is this thing in brackets? Well, that's just a covariance between the two random variables. So now we have this next important property for the variance, and that is the variance between x plus y is equal to the variance of x plus the variance of y plus 2 times the covariance between x and y, right? So that's the general formula, and that's true for all random variables x and y. But there is a special case. What about when x and y are independent? So if x and y are independent, then we know that the covariance between them is equal to 0. So if the covariance between them is equal to 0, that's going to delete that last term. And then we get a special case for the variance formula. So the variance of x plus y is only equal to the variance of x plus the variance of y if and only if the random variables are independent. All right, so make sure to test independence if you want to use that cute rule, else you have to use the covariance formula, which sometimes is a little time consuming, but not impossible. So those are the main important properties of the expected value, variance, covariance, and also a little bit of introduction on the correlation and the product moment between two random variables. So stick around for some practice concepts and applications for these things, and I'll see you in the next lecture. See you later.